Uh, in this video, I will be talking about elementary signals. In the previous video, we talked about the types of or classes of signals like odd, even, periodic, random, deterministic, continuous time, discrete time. Now we will be talking about basic uh, literature, basic terminology about signals arkadaşlar. So when we talk about signals, it's like an alphabet that we use in our language, like A, B, C. We put them together and come up with certain words. So here now we will be learning about certain elementary signals which we will be using throughout the whole subcomponent. That's why I want you to be ready to learn these and do some exercises on those signals. Okay. In this video, I will be mainly talking about these elementary signals. So let's start with step function. If you think about step function, like in Turkish we call it basamak fonksiyonu, it is very easy. Okay, if you look at this at 0 time instant, it will become 1. It's just like a stairs. Okay, so we represent it with u of t. It is 0 before 0. It is 1 after 0. For all values after 0, it is 1. For all values before 0, it is 0. Okay? There is an immediate jump at this point. So we will use this step function throughout this subcomponent. If we shift this signal, then it will be like that. Okay? So what does it mean? If I shift means kaydırmak. Okay, kaydırmak. If I shift my step function by a seconds, then it will be like after a seconds, all the values will be 1, and before a seconds, all the values will be 0. Okay, that's critical here. So I want you to understand the main ideology behind step function. Let me remind you one thing. For example, I will take this one and take it out and then say t will be greater than 0, it will be 1, t less than 0, it will be 0. Similarly, I will take this one out and say t minus a will be greater than 0. And then we will say t greater than 0. If this is true, my output will be 1. What does it mean? T greater than a seconds, after a seconds, for all time instants, my voltage will be 1, or my value will be 1. Okay, so I hope you understand the step function. If we talk about another very important function that we will be using in this subcomponent is called impulse function or Dirac delta function. We will use both of them interchangeably. Okay, impulse function or Dirac delta function. So what does it mean? If we, that's the definition actually. Okay, if we have a rectangular pulse like this, which is like 1/2, like minus 1/2 seconds here, 1/2 seconds here, and the amplitude is 1. Okay, the area under this gray zone will be 1. If I squeeze my rectangular pulse to this point, and this will be like 1/3, 1/3, minus 1/3, and now I will have 2/3 as my width here, and it will be like 3/2 as my amplitude. So the area under this will also be equal to 1. So if I go smaller, smaller, smaller in terms of width, I'm decreasing the width. Okay, decreasing the width. So as I go further and further and make the width smaller, keeping the area as 1. Keep the area as 1, okay? Area should be 1. So I'm decreasing the width. Let's say if my time or the width becomes 0, the strength will be equal to infinity. But the area, let's say the amplitude will be equal to infinity, but the strength will be like 1, okay? So this is a mathematical tool that we will be using in this subcomponent. What does that mean? It is like an instant change, like without any time, there is an instant change. That's why we use Dirac delta function, okay? So this is very critical. The strength, as I mentioned here, now we are decreasing keeping the area fixed. The time will be collapsing. If the area is not 1 but A, then the strength will be A, okay? So this is like strength is 1. The area means the area under it is 1. Here the area under this curve is 1, not 1 but A. Then I will say this is Dirac delta function with a strength A, okay? The area under this is A. So we will use this integration all the time. The area under this function, Dirac delta function, is always 1. This is the area, okay? This is why we use this from infinite, minus infinity to plus infinity situation, okay? For example, this is true for this box, right? Rectangular signal. It's also area is 1. So for this, also from minus infinity to plus infinity, the integration will be equal to 1. Okay? So this is the definition of Dirac delta function, impulse function. It is 0 for all t is not equal to 0. You see here, nothing. It is 0 all the places, 0, 0, 0, 0. But at this point, we don't say the value at this point is 1, but the area under this point time is 1. Okay, this is critical. Its value is not 1, but its strength, the area under this function, is going to be equal to 1. Okay, the amplitude is infinity, width goes to 0, so my strength, the area under this, will be equal to 1. So I hope you got the main idea. So let's a little bit move further. I will have this box here, this rectangular signal. What is happening here? There is an immediate jump at this time instance, minus t, and there is an immediate drop at time instant t. So there is an increase, instant increase here, and instant decrease at this point. Okay? If we now make this width smaller and smaller and let this width go to 0, then it will be like this. 2 arrows like that. One arrow is up, one arrow is down. So if I talk about the derivative of the Dirac delta function will be something like that. So Dirac delta function is like this. Okay, strength is 1. At time 0, it's happening. But for Dirac delta function's derivative, it will be something like that. Okay. So let's move further. If we talk about the Dirac delta function or unit impulse, we also call it unit impulse signal. Okay, this is unit impulse signal, impulse function. These are the names: unit impulse, unit impulse or Dirac delta function. Okay. So these are the things that we are talking about. So there is one. Let me remind again, the area under this thing is equal to 1. Okay. So I would like you to understand this relationship between unit step function and unit impulse function. Okay. What's the relationship between these two? If I take the derivative of this unit step function, what is the derivative at this point? There is no change, there is no slope. That means the derivative at this part is 0, because there is no change in the values. There is no change in the values here, so the derivative is going to be 0. But there is an instant change. Instant change means there is an instant jump here, and this jump is going to be represented as this impulse, unit impulse signal or unit impulse function. Okay, so what do I tell you here? The derivative, let me come back here. The derivative of u of t will be equal to Dirac of t. Okay, so if I take the derivative of this signal at time equal to 0, it will be an impulse signal. At all other points, the derivative is going to be 0, but at time instant equals 0, it will be equal to Dirac delta function. If I take the integral of both sides, then I will say u of t is equal to Dirac delta function, Dirac delta function's integral. Okay, so there is a relationship between these two. If I take the derivative of the step function, I will get impulse. If I take the integral of impulse function, then I will obtain unit step signal. Okay, this is very critical. I hope you understand what's going on. So this was for continuous time signals. Now let's go into unit impulse and unit step signals for the discrete time case. So it is important for you to understand, like, this was my discrete time representation, and I say Dirac of t. Here I will say Dirac of n, and its definition is every time instant, every sample, I have 0. Every time instant other than 0, everything is 0. But at 0 sample, my value is 1. Okay, this is the definition. When n is not equal to 0, the value is 0. When n sample number is equal to 0, my output, my function is 0. So this is called unit impulse, discrete unit impulse signal. So it is very important. Similarly now, when we talk about putting all these signals, so if you think about unit step signal, what does it mean? After n is greater than or equal to 0, the function is going to be 1. You see, 1, 1, 1 for all n's. My value is 1 for u of n. For all values that are less than 0 will be equal to 0. So in discrete time, when we talk about differentiation or integration, now for the differentiation we will be thinking about difference. like this one. Or when we talk about integration, we will be talking about summation, okay? When we talk about differentiation, we will be talking about taking the difference. For the integration, integrals, it will be converted into summations, okay? So for the unit impulse function, if you look at this one, what does it mean? U of n minus u of n minus 1. So I don't want to go into detail right now. I will talk about that in the later slides or in the later videos. But this is something like shifting, and I will talk about this shifting in coming slides. Okay, so I don't want to go into too much detail right now because I want you to know first the shifting and other details about signals right now. And finally, let me show you, until now, we talked about U of t, we talked about Dirac t, we talked about the derivative of Dirac t. And this is the final basic signal, elementary signal that I would like to talk about, which is called the ramp function. Okay, ramp function is this: 0 before 0, and then is equal to t when it is greater than 0. So if we define it, r of t is equal to 0 when t is less than 0, it is going to be equal to t when t is greater than 0. For the continuous case arkadaşlar, for the continuous case, equal to, we don't use it too often. We just say greater than or less than. Okay. So if we take the derivative of this, what is the derivative of t? 1. Before 0, it is already 0. There is no change. Derivative means rate of change. After 0, the slope is like 1, 1, 2, 2. The slope is 1, right? So the slope here is 1. So what does it mean? U of the derivative of r of t is equal to u of t. The derivative of u of t, as I mentioned before, will be unit impulse function. And also derivative of unit impulse function will be Dirac prime. This is called derivative, okay? Maybe you remember from calculus. That's all for the elementary signals arkadaşlar. And when we meet, we will do some exercises on these elementary signals, and we will work on the manipulations on these elementary signals. See you in the next video and in the class.